This problem is looking at finding the electric field of a very thin plastic rod that is uniformly charged. The first part of this problem asks us to consider an arbitrary piece of rod length dx located at a position x on the rod. Determine the electric field dE from this piece at observation location asterisk, a distance w to the right of the rod and on the x-axis. This diagram here was given to us. However, I did pick an arbitrary value here just to represent dx. It doesn't really matter where you pick because it is arbitrary, which will then give us that this length here is going to be x. And then later on we'll figure out, but you can also deduce this from your findings here, that this length from the dx, the asterisk, is going to be L plus W minus X. So next what we're going to do is we're going to find our R value. So we're going to do that by finding the R of the observation location, which is going to be right here for us, and the R of the source, which is the dx. So it's going to be the R vector of the asterisk minus the R vector of the dx from the origin. So the R vector of the asterisk is going to be this whole length here. So that's going to be L plus W in the positive x direction, and then 0, 0 in the y and z directions. And then we're going to have, for the dx R vector, we're going to have this value here, which is our x, 0, 0. So then when you do that math, you're going to find out that our R vector is going to be L plus W minus X in the X direction. Then we're going to go ahead and find the magnitude of our R vector, which is going to be our R that we found here, each component squared, and then the square root of that. And since we only have one component, it's going to just end up being that component itself. Then to find our unit vector R, we're going to take our R vector here, and then we're going to divide that by our magnitude. So that's going to give us this here, and when you do that math, you're going to find that our R hat, or our unit vector, is 1, 0, 0. Next, we need to find the charge density to help us determine the electric field dE. So what we're going to do is, because this rod is very thin, we are going to treat it as a line. So we're going to use lambda for our surface density, which is just the charge over the length. So our charge given up here is a positive Q, and our length of the rod is going to be L here. So that's going to be our charge over length. And then we also know that lambda is equal to dq dx. That will give us this equation here. And then just switching that around to solve for dq, we're going to get dq equals the charge over the length dx. Next, we can go ahead and take this value here and put it into our known equation for the electric field of the point charge, which is going to be the constant 1 over 4 pi epsilon naught dq over the magnitude of r squared times the unit vector. Then plugging in our value for dq up here into this equation, we find that we get 1 over 4 pi epsilon naught q over L times dx, which is just plugging this in for dq over here. We get that over L plus W minus X, which is just our magnitude that we found up here, squared, times the R vector that we found earlier. So just putting that all together, this is our vector for the electric field dE. And then the second half of our problem is going to ask us to solve for the net electric field E of the rod at the observation location. And we're going to have to do this using an integral because the electric field is changing over the distance. So we know our equation is going to be that it's the integral of the dE that we found before, and then using our diagram from the previous equation, we know that the length of our rod is going to be from the origin all the way to the end, which is L. That's going to be our values here. And then we're just going to go ahead and plug in that equation that we found that we just solved for right over here. And then the next step we're going to go ahead and do is take out everything that we don't need in the integral, which is going to be anything not involving x. So we can go ahead and take out this 1 over 4 pi epsilon naught and then our q over L, and we can also take out this x here because this is just the unit vector giving us the direction and nothing that we actually need to integrate. So in the integral, that's going to leave us back with dx over L plus W minus x squared. And to integrate that, you can do a couple different things. You can go ahead and just use rules of integration to solve that. I'm going to go ahead and use u substitution just so I don't get confused. So I'm going to have u equal L plus W minus x and du equal negative dx so that our signs work out in our favor in the end. So doing this, we're going to substitute in here. So our dx is going to be a negative du. And then our bottom denominator is going to be just go to u squared. We can take the negative out of this and go ahead and say that this is u to the negative 2 du. And then when we integrate that and put back in that negative sign, we get negative u to the negative 1 over negative 1, and these negatives cancel out, giving us 1 over u. So then when we plug in our original values, we're going to get that the integration of our dx up here is going to be 1 over L plus W minus x. So then we can go ahead and keep solving for our total equation that we had here. We go ahead and put back in that all that stuff that we took out of the integral. We're going to put that before. We keep our 0 to L, and then we go ahead and put in that integration here. So we have everything we took out times the 1 over L plus W minus x, and then we're going to go ahead and solve that from 0 to L. When we plug in those values, we get 1 over L plus W minus L minus 1 over L plus W. We can go ahead and simplify that here to get 1 over W minus 1 over L plus W. And then we're going to go ahead and find a least common denominator, so we can go ahead and add up these values here, which leaves us with the L over W times L plus W right here, times all those things that we took out of the integral at the very beginning. When we put that all together, we're going to go ahead and get this here, but that's a little messy, so I'm going to go ahead and clean that up a little bit, and I'm just going to put it as that E is 1 over 4 pi epsilon naught. I just took that out because that is a constant and it's something we can recognize easily as a value, times Q over W times L plus W in the x hat direction, or we can go ahead and write it as the vector here.